In this section, we're going to talk about potential energy, but before that, we should have an introduction to conservative and non-conservative forces, because the concept of potential energy is tied to conservative forces. So what is a conservative force? A conservative force is one which work done by the force is independent of the path of the object. So work done by the force is independent of the path taken by the object. It only depends on the initial and the final positions. In order to understand this, let's take an example of a conservative force. Gravity is an example of a conservative force, which means that the work done by gravity is not going to depend on the path taken by the object, but it depends on the initial position of the object and the final position of the object. So let's look at an example. So say I have a mass m lying on the ground and I'm trying to lift it or move it to a position m that is at a height h from the ground. So in order to do this, I need to apply a force and lift it at a constant speed and then move it to this position. So what is the minimum force required in order to lift this object? So if you look at the free body diagram, there is gravity acting on the mass, which is mass times acceleration due to gravity, vertically downward. There is my applied force, which is going to be acting vertically upwards. And the minimum force that I need to apply is just equal to mg. So we want to calculate what is the work done by gravity as it is moved from this position to this position. We know that work done is equal to, work done by any force is equal to force times displacement times cosine theta. So we want to calculate the work done by gravity. So, and that will be force of gravity, which is mg, times the displacement, which is the height, times cosine of the angle between the two vectors. Notice that gravity is downward, whereas the displacement is going to be an upward vector. So the angle between the upward direction and the downward direction is going to be 180 degrees. So this is cosine 180. So that means the work done by gravity is negative m times g times h. Notice also that at the same time, the applied force does an equal amount of positive work because the applied force is in the same direction as the displacement. But we want to look at the work done by gravity, which is equal to negative mgh. And if gravity is a conservative force, it shouldn't matter how I take the object from this position to this position. I might take it straight up or I might take it down a winded path, but the work done should still be the same. Is it? Let us find out. So instead of taking it straight up, what if I take it through a path, which is I move it horizontally this much, and then I move it vertically this much, and then again I move it horizontally, and then I move it vertically, like this. So let's say this height is h1, and this height is h2, and this distance is x1, and this distance is x2. Is the work done in taking the mass by gravity, is the work done by gravity in taking the mass through these winded path the same as the work done in this vertical path? So let's find out. So in the first instance, for the horizontal, the force of gravity is acting straight down, but the displacement is going to be horizontal x1. So what is the angle between the two vectors? Yes, 90 degrees. So what will be the work done in this case? If theta is 90, cosine 90 is going to be 0. So the work done during this path is going to be 0. Same is the case here because the force is straight down and the displacement is horizontal. So force is perpendicular to displacement. So horizontal paths, there is no work done. What about the vertical? In this case, the work done is going to be, because the gravity is straight down and your displacement is straight up, the angle is 180. So the work done in this case is going to be mgh1 with a negative sign. By the same token, the work done in this case is going to be negative mgh2. So in order to get the total work done in taking the mass from this position by this winded path to this position, the net work will simply add all the work done, which is 0, negative mgh1, 0, negative mgh2, which will be negative mgh1, negative mgh2, which can be written as negative mg h1 plus h2. And we can see that h1 plus h2 is just equal to h. So which is just negative mgh. So notice that even in this case, when we have a different path, the work done is still the same as the previous one. So this argument can be extended even if you have a winding path like this, because any such path can always be broken down into horizontal and vertical displacements, and the work done during horizontal displacements is always going to be 0. But the work done during vertical displacements will add up to give the same thing. So since work done is independent of the path taken, therefore we can say that gravitational force is a conservative force. So with such a conservative force, then you can associate an energy with the configuration of the system or with the position of the system, and that is what we call as potential energy. Let's come back to that a little later. We want to see what is a non-conservative force then. A non-conservative force would be, an example of a non-conservative force would be friction, which means that the work done by friction will depend on the path. So let's just take a quick example of an object, say like a car. Something like this. Looks like it's moving the other way, but let's say it's moving this way, and it's moving from here to this position where the displacement is going to d. This is the direction of the velocity. So the work done by friction, of course there are other forces acting on the object, but we know that friction is going to be opposite to motion. So this is our Fk. So the work done by friction will be force times displacement times cosine of the angle between the two. And we know that the cosine of the angle is 180 degrees, which is cosine of the angle being negative 1 because theta is 180. So the work done by friction is minus Fk times d. What if we change the path a little bit? What if instead of going straight like this, the car went this much and then retraced back and then again this much? Is the work done still going to be the same, or is it going to be different? So during this path, let us say d1, the work done is still going to be, friction is this way and displacement is this way. So it's going to be negative work. Let's talk about this way, this path. So when the car is going this way, friction is going to be, displacement is going to be this way, but friction is still going to be opposite. So therefore it is 180 degrees to displacement. So the work done is still negative. Again, when the car moves in this direction, so displacement is this way, friction is this way. So again, the work done is going to be negative. So all of these work dones are going to just add up to something that is more than this, because it's going to be negative Fk times d1 plus negative Fk times d2 plus negative Fk times d2 plus negative Fk times d3. So this is certainly going to be more than this. So therefore work done by friction is not independent of the path, and the longer the path is, the more work friction does, which means that if you were to if you had a slide that was like this and you had a slide that was like longer, then the work done by friction during this slide 2 is going to be more than slide 1, because this is a longer path. So during all of this path, work will be done in opposing frictions, so therefore a larger amount of work is done in this path than in this path, even though we can say that the initial and the final positions or the altitudes are going to be the same. So friction therefore is an example of non-conservative force, which means that we do not associate a concept of potential energy with it, because it cannot be associated with one configuration, because it depends on how it was brought to that place. So let's go back now and use the concept to look at what is potential energy. So potential energy is any form of stored energy. How do we store energy in an object? So stored energy stored due to some previous work on it. So energy stored due to some work done on the object is what we call as potential energy. There are different forms of potential energy associated with different conservative forces, like elastic force in a spring is a conservative force, so you can have elastic potential energy. Electrical force between two charged objects is a conservative force, so you can have electrical potential energy, and so on. But we are now just going to look at potential energy is associated with the work done against the force of gravity in changing the position of an object. So let's look at the same example that we used before. So I have a mass m that is on the ground, and I'm going to lift it up through a height h and put it in this position. Now the work that I do is going to manifest itself as a change in the potential energy. So I'm going to write work done as delta, which stands for change, and U is the potential energy. So work done is the change in potential energy. And we talked about how in order to lift this up, the minimum force I need to apply is just equal and opposite to the downward force of gravity on it. So F is mgh, and F is mg, and the displacement is the height. So work done is simply, starting from the original equation FD cosine theta, we substitute work done by the applied force is mg times the displacement is h. Because my applied force and the displacement are going to be in the same direction, angle is 0, so that gives me the work done as mgh. So that means this is going to be the change in the potential or energy of the object between these two positions. So delta U between positions A, let's call this position as A and call this position as B. So delta U, which is potential energy at point B minus potential energy at point A, is equal to mgh. So what if I set the potential energy at point A as 0? So that means I'm going to choose this as my reference level, the ground, and say arbitrarily that potential energy on this level is equal to 0. Can I do that? Yes, of course, because everything is going to be relative, so it becomes convenient to set the potential energy to 0, so that then we can write UB is simply mg times h. So that means the potential energy of any object, gravitational potential energy of any object, is given by the mass times acceleration due to gravity times the height of the object measured from your reference frame. So your reference frame is nothing but your choice of 0 potential energy. So in any problem situation, the choice of 0 potential energy is completely yours. So if suppose I'm doing some experiments inside the classroom, so say this is the ground and then you have a table. So if I choose this as my 0 potential energy, that means an object here or an object here will have positive potential energy relative to the ground. But if I choose the table as my 0 potential energy, then that means an object on the floor is certainly going to have negative potential energy because it's below the zero potential energy, whereas an object